Hi, I'm Carter Schultz, and this is Fundamentals of Engineering, class number 4, Mechanics of Materials. This is a re-recording of a class that was done live, but had some people miss it and some technical difficulties, so this will hopefully be a quick and effective recap. The objective of this class is to basically condense what is a freshman, sophomore level Mechanics of Materials class at the university level into a single lecture, giving a broad overview of the topic as effectively as possible. So this is part of the Solid State Depot's summer class series. Solid State Depot is a 501c nonprofit makerspace in the Boulder, Colorado area. It currently needs more members, needs some help. We're doing a drive. Donations are great. Please check out ssdmakerspace.org, but new members are better. So if you're interested in joining and becoming a sustaining member of the space, please do so. So who am I? Hey, look at my face next to my face. I've been a member of the Solid State Depot for about 6 years. I've been on the board for about 4 of those. I am a professional robotics engineer. I'm originally a mechanical engineer, but do software most of my time. I've worked at SpaceX, Anea Systems, which is a robotics research company in Pittsburgh, and I'm currently the robotics architect for AMP Robotics, where we build recycling sorting robots. I also heavily mentor FRC teams. So here's me with 2036, which is the high school robotics team that operates out of the Solid State Depot. So big summary slide to say I build a lot of robots. I am by no means like a true expert in the subjects we're covering, but I have a lot of practical knowledge with them. So this is part of a micro degree class. So there's 8 classes in total. If you attend and participate in 6 out of 8 of them, you get a degree at the end of it, which is great. There is no final project. That idea was scrapped, so we can cross that out. And today we're talking specifically about mechanics of materials. So to really talk about mechanics of materials, we do have to understand the concepts of forces that are acting inside of materials, which is really just statics. I would say statics is the only kind of prerequisite knowledge for this, but hopefully if you're coming in without knowledge of statics, it won't be too crazy. So mechanics of materials is fundamentally about understanding how real world materials respond to forces. We want to know when objects experience forces, how they're going to change shape, and we also want to know when an object will fail from kind of the engineering definition of failure. And failure in engineering sense usually means one of 2 things. Either the part changes shape permanently, so it's no longer going to be the same shape. We call that plastic deformation. Plastic deformation is permanent change in shape, as opposed to elastic deformation, which is where the material temporarily changes shape under load and then springs back. It like a piece of elastic returns to its original shape. So that's the first kind of failure mode is permanently changing shape. But also we can consider a piece to often have failed if it changes shape enough that it interferes with the rest of the mechanism. So if the tip of the fan blade deflects enough from the wind forces that it hits the cowling, bad day, our design has failed. So this entire kind of lecture is going to be around the idea of understanding when are things going to fail and how are they going to change shape when forces are applied to them. So brief overview of like what topics we're going to hit. Stress and strain are the fundamental kind of concepts and units of talking about what's going on inside of materials. So we'll introduce the concept of what stress is, we'll introduce what the concept of what strain is, and then we'll talk a lot about the stress-strain curve, which is the relationship of how these interact inside of the material. We'll talk about the actual like atomic model of how to think about what these quantities are representing, and then we'll talk about the von Mises stress and shear stress versus normal stress, where von Mises is the main failure criterion for assessing whether a material will experience permanent deformation. And then we'll briefly cover some examples of how to calculate stress in different circumstances. Again, this lecture is not aimed at equipping you with the full knowledge of a mechanics and materials class, but it's hoping to cover the rough concepts of everything that that class will go over, either if you've taken a mechanics and materials class before as a refresher, or if you're like a high school student interested in doing a mechanics and materials class, this is kind of an overview of what you'll learn in that class. So The first thing that we want to do is, I think it's massively helpful if you have some intuition for the things that we're talking about. So we're going to do a little mental experiment, and this is like the first thing to think through. We have a 1 centimeter by 1 centimeter square rod, so just one by one, and we're going to make it a nice long rod like this. So that's kind of the cross-sectional area of it, and then this is a top-down view, and I'm drawing on my tablet at an angle here, so this is not going to be pretty drawings, but hopefully a little bit better than this. Oh, this is awkward. So we're hanging a weight from that rod, and we do one test, and we find that when we put 100 newtons of force on the end of that rod for whatever magic material that we're doing this experiment with, the rod snaps. Now, if we make a different rod that instead of being 1 by 1, it's now 2 by 2, and we repeat the experiment, and we apply force until it snaps, the question now is predict what is the force that that rod will snap at, with the rod being dimensionally twice the size. And if you've worked with materials before, if you've kind of been exposed to stress, I don't think the result is incredibly surprising, but like this is the most fundamental intuition to kind of build up as to why the concept of stress exists. And the answer here is that the force will be not 2 times as much, but it'll actually be 4 times as much. It will be 400 newtons. And the reason for that is that this shape has actually 4 times the area of the original shape. There's 4 of the little 1 by 1 cubes in there. And when we do just general tension experiments where we pull on materials, we find that the thing that most predicts when that material will fail is, or when an object will fail. Let me say what predicts when an object will fail is kind of the cross-sectional area of that object that force is being distributed over. And that's where the concept of stress comes from. So like in the real world, engineers repeated experiments like this where we put objects under loads and we pulled on them until they broke, and we did this over and over and over for thousands of experiments, and we found out that regardless of shape, generally, like things get messy with a lot of this, but regardless of shape, if we did 3 objects, and let's say we circle, triangle, square, let's say we do a pipe, we do something like this, if all of these shapes have the same area, then roughly, if they're made out of the same material, they'll be able to withstand the same amount of force. And so we discovered this relationship between the area of the cross sections of the object and the force that object could encounter, given that it's the same material. This is what stress is really trying to represent. It's representing this idea that you go out experimentally and you find that for the same material, objects of the same cross section, when pulled in pure tension, will snap at the same amount. So the formal definition of stress isn't more complicated than this. It is force per unit area within kind of the internal structure of a material. And the important part about stress is, like, when we want to talk about a very complicated engineering shape, like a piston or a crank, and there's flanges and there's weird things going on, we want to predict when that's going to fail versus a slightly different shape. We have to somehow normalize what's going on inside it to the shape of the thing. We want to be able to take the actual shape out of it and talk purely about something that is independent of shape, and that's where this idea of dividing the force by the area comes from. And I think it's pretty easy to imagine like why stress works if we think about, like, we've got two sides of the material and there's individual atoms in here, and these individual atoms have bonds and they're kind of holding on to their neighbor. And this is not actually what's going on inside the material. Materials are way more complicated than this. Quantum dynamics are wild. Chemistry's funny, but it's a really good mental model for thinking about stress. And what's going on here is that the more area we have of the material, the more we kind of continue this off to the side, the more atomic bonds there are in there to share that amount of force. And so the force per individual bond is kind of what stress ends up equating out to. And so stress is not like a fundamental quantity of the universe. It's not like an SI unit. It's an engineering model for normalizing force over the shape of something. So that's the formal definition of stress. Now, I said it earlier, and I'll say it again. nothing's ever as clean as we want it to be in engineering. So let me make my head a little smaller. Nobody really cares what my face looks like, so I can get out of the way of the text. In reality, things get way more complicated than this, but it all just comes from expanding that idea of stress out more and more and more. And the reality is, these stresses within a material don't just magically even themselves out. Instead, the stresses kind of flow through the material. And right near the actual, like if we pull right at one point at the base of this object here, the stresses will have a really sharp peak where most of the stress is being concentrated right at the very center where we're pulling. As we get further away from it, the cross section kind of smooths out, and if we get sufficiently far away, it actually does equalize out, where there's no extra roads in this, extra stresses in certain areas. A nice example of this is like rock climbers or highliners that use Dyneema slings, where Dyneema is like a very strong material. You have this incredibly strong woven rope, and this is me drawing a woven rope. Well, if you just tie a knot in the end of it, or you just try to like anchor a few of the strands, you'll find that you'll lose something like 70 or 80% of the strength of the rope. And that's because you're getting these stress concentrations in individual strands, or individual locations in the rope get too much load on them, and it causes the rope to fail at a much lower force than you'd want it to. So what they end up doing is they take the rope and they tie a big loop in it, and then they thread the rope back through itself, and they do this kind of basket weaving approach where for a tapered section of the rope, this is the worst drawing I've ever done in my life, but whatever, art. But they taper the rope back into itself and weave it into itself so that the force is transitioned over a large area of it there, where for a big section of the rope, it's effectively twice the thickness. And by doing that, they get out of this nasty zone where there's like stress concentrations, and wait until the forces inside of the shape have really equalized before going to the main diameter of the rope. And by doing so, you can get way more strength. So again, we'll generally today talk about this like approximation where the forces are uniform inside it, but in reality, these forces kind of flow through the material, and there's a way that they flow that you get into fancier engineering and it matters more. So in previous classes, we introduced the idea of scalar quantities, where a scalar quantity has a single value and it's just, a number between 1 and infinity or whatever. It's a real number. I'm bad at actual math terms, but we have a scalar that's just a number. We then have a vector quantity, which is a number with some direction, right? So we can have like an XYZ. This can also be written as something like a radius and an angle. But these are scalar quantities. I don't really want an equal sign there. So we have scalars, we have vectors. Well, when we actually talk about stress in a material, the stress isn't a single value or even a single direction. Instead, stress is one of the first tensor quantities that you get introduced to in engineering, where the actual way that we represent stress inside a material ends up being this thing called the Cauchy stress tensor, which has a bunch of terms in it, and the diagonal terms are normal stresses, and the off-diagonal terms are shear stresses, and it's a symmetric matrix, so there's not actually 9 unique numbers in there. The shear stresses are mirrored against each other, and that actually comes from statics. But why this occurs is the plane that you decide to kind of cut the shape on determines the stresses that you would measure there. So like if we had our rod from earlier, well, we took a cross-sectional area that was kind of perpendicular to the forces, but we could imagine, instead of asking about the forces on that perpendicular face, we could cut at an angle, or we could cut at any direction. And the Cauchy stress tensor represents this in a in a way that is invariant to the direction. So the Cauchy stretch tensor, as you write it, will have some fundamental orientation to it, but we're able to rotate it in any frame. And what it really is, like the mathematics here is complicated. I don't think the fundamental concept is that hard, but we take our object and we have some complex object and we break it into a bunch of cubes. And this is exactly what finite element analysis is. This is what lots of engineering software is used for, but we break the object into a bunch of tiny little cubes, and we look at one of those cubes, and that's kind of the diagram on the left here, and we say what must be the forces on each face of that kind of infinitesimal cube. And the various terms of the Cauchy stress tensor are just the various forces on the faces of this cube. And the Cauchy stress tensor fully describes the stress that's occurring at one location in an object. And when we really talk about stress, like to talk about it mathematically properly, you can't talk about it as a single number. You talk about it as this stress tensor. We're going to come back to this a little later. That's really just introducing this idea of what is stress. Well, we're talking about the forces that exist on an infinitesimal little cube of our material, and there's forces on different faces depending on the orientation of it. Not the best explanation I've ever given for something, but hopefully gets the concept across. And again, we're gonna simplify now and talk about what really matters. The important thing to remember when talking about stress is that any kind of load that we place on an object produces internal forces. From statics, if we kind of cut a system boundary through that object, we would find that across that system boundary, there must be forces that counterbalance to keep the object from accelerating. And so those internal forces get distributed across the shape of the material. The more actual material we have, the more meat we have in our object that shares the force, the less force is seen by any individual point. And this is really critical because the force seen by an individual point is what predicts a lot of our failure criterion from the beginning. So we're going to put a pin in stress. We're going to go instead and talk about strain, which is we'll get there. We're going to come back and kind of put them together in a little bit. So we'll put a pin in that. Now we're talking about strain. And one of the things that I think is annoying about engineering is that we use a lot of words which are common language words, like, oh, I'm really stressed today. Oh man, that person's under a lot of strain. Those words have common definitions that aren't very precise. So like, what does it mean when someone is stressed? What does it mean when someone is strained? Well, in engineering, these are very, very, very specified terms, and people understand, like, when you say stress in an engineering discipline, there's only one thing you're talking about, and it's force per unit area. Same thing with strain. This is just me on a tangent about language, but it's fun. So same kind of mental experiment that we did earlier, and we're now thinking about the stretchiness of materials. And what we find is that no material, literally nothing, not even diamond, which is one of the like stiffest materials that is out there, is perfectly stiff. What we find is if we do any kind of experiment where we repeat what we were doing earlier, where we have some kind of test material and we hang a weight off of the end of it, well, if we measure the length that it started with and the length of it while the force is applied to it, and we'll call that L2, we find that every material stretches a little bit when you put some force to it. But the data doesn't quite make perfect sense. So if we start with, we have a 100-meter rope. So we have a pretty long rope, and I hang some load from it, and I find that when I measure it again, it's now 101 meters long. Okay, that's not crazy. And well, what happens now if we take a 200-meter length of the same rope and we put the same load on it? What does it stretch to? Think about it for a second. Again, I don't think the intuition's too surprising here, but it's kind of a crazy fact to learn if it's the first time you're exposed to it, which is this is now going to stretch to 102 meters. And there's really easy intuition for this again, which is I now have a 100-meter rope, 100-meter rope attached to a 100-meter rope. That's what a 200-meter rope is. Both of those 100-meter ropes are seeing 100 newtons. Oh, I wrote a 2 there. 100-meter ropes are seeing 200 newtons of force. which means that the first one stretches to 101 meters, the second one stretches to 101 meters, and the final length is 202 meters. Dang it, I wrote 102. I probably said 102 earlier. It's 202 meters. And the intuition to build here is, right, we have atomic bonds in a chain kind of running down. And as I pull, every single bond in that chain is going to stretch by some percentage of the distance between the materials. And the more bonds I have in a chain, like every single bond in this chain is going to see the same amount of force. Like at every cross section, the force will be the same. Every one of those bonds is going to stretch by some amount. And the more bonds I have stacked together, the further something is going to stretch. And so if I double the length of something that I'm pulling on it, I will double the amount it deflects under the same amount of force. And that is what strain is. So the actual engineering definition of strain, and it's a little weird because it ends up being a unitless quantity, but it's the change in length per unit length that something encounters. And so if I have a 100 meter thing, and that stretches to let me write it like this. I'm going to say 101 meters was our L2. We started with 100 meters and our initial length was 100 meters. We find out that this is a 0.01 strain, and everything's meters here, so the meters cancel out and strain comes out unitless. We often talk about strain as a percentage. So we might say this is a 1% elongation of the material. And that's, again, this is another way of talking about how materials change shape, or how objects change shape, that is trying to remove the shape of the material from it. So we can talk about it in like an abstract of the shape of the actual thing we're designing. The strain will be constant for some amount of force that's going on in there. So that's the fundamentals of strain. And again, I think the having this idea that our materials are really just a bunch of little balls connected with springs, that is the best mental model to initially think about what's going on with the material, where we have individual atoms. These atoms are connected by atomic bonds, and the atomic bonds themselves are a little bit stretchy. It's grosser than that, but it's a really good approximation for thinking about things. So this idea of mental experiment that we've been doing is actually a very, very real experiment. Basically, every engineering lab has one of these machines in its basement, and companies make these and sell thousands of them, and there are probably tens of thousands of these material tests that are conducted every day around the world in hundreds of labs. And the way that the actual test works is we take a specimen that is prepared. Usually they're cylindrical because it helps some of the weird squirmy details get put in a way. And the material's long enough that, the forces are normalizing in the cross section as we get in there. But we put it into a machine that gradually increases the amount of force that is being applied to that material while very precisely measuring the change in length of that material as it goes. When you do that, and you normalize for the cross-sectional area of that material and the length of the sample that you start with, so that we're kind of comparing results of machine A to results of machine B, we find that we get this stress-strain curve for a material. And what's going on here is that the material is gradually stretching out and elongating, and as it elongates, the amount of force that's going on is increasing to make the material elongate further. This single curve defines or well describes all of the material properties that we talk about. So the next few sections that we're going to go through is basically talking through the actual properties of materials that if I go and look up, 6061 aluminum online, I will find a yield stress and an ultimate strength and a maximum elongation from it. We will understand where these terms are coming from and how they're used. So Generally, and this is for well-behaved engineering materials. Things get really messy when you get into stuff like composites and carbon fiber and fancier materials. We're not going to dive into that complexity yet, but generally the stress strain curve is a fundamental property of a given material. So if I have 6061 aluminum, which is like, this is a particular alloy of aluminum, if I measure its stress strain curve, that curve will be constant, or at least constant enough that engineers can very, very, very well design around it and design very complicated things, assuming that stress strain curve is what it is. And so if we understand this stress strain curve really, really well, good things happen. I feel like the slide's a little redundant with the last slide, but whatever. Oh no, I haven't erased everything from last time. Avert your eyes while I erase away, and then we're gonna retry it all. So the first region of the stress strain curve that we're going to talk about is what's referred to as the elastic region. And if we look at the stress, we'll go back to the slide of the other gate. If we look at this first section here, there's a straight line. And the straight line goes up and to the left, or up and to the right. Why can't I speak? And it is perfectly straight, like ludicrously perfectly straight. It is a linear property, and it remains straight up until some point where everything goes curvy. So this first region where everything remains nicely linear is the elastic region of the material. And that's what we're going to focus on right now. So the elastic region has some kind of slope to it, right? Where there's a line going up. Some materials will have a high slope of it. Some materials will have a middle slope for it. Some materials will have a lower slope for it. But every material has some linear slope in that initial region. This is what engineers mean when they say that a material is stiff. We are talking about the slope of the stress strain curve in this elastic region. And a material that has a high slope here is a stiff material, and a material that has a low slope is I'm just going to say not stiff material. And this, the slope of the line in the elastic region is referred to as the Young's modulus, otherwise known as the modulus of elasticity. There's supposed to be a U in there. And I see both used pretty commonly. I think older textbooks use Young's modulus more, and modulus of elasticity is slightly more common, but like the Wikipedia page is Young's modulus. Modulus of elasticity, I think, redirects to it. Either name is in pretty common usage. And it is defined as, the y-axis of our graph is stress, the x-axis is strain, so the slope there is stress over strain. Stress has units of force per unit area, and strain is unitless, so you end up with a force per unit area, which is also the units of pressure in SI. So the units are usually given in pascals or PSI, but the numbers are very, very big for most of the materials we work with. So looking at this kind of chart copied from Wikipedia here, we can see that aluminum has 68 gigapascals, 10 to the, oh God, I hope that's billion. I think that's billion. I'm not gonna prove my ignorance by committing to that answer, but I'm gonna guess 10 to the ninth, probably. We'll find out. Someone will correct me. So aluminum, 68 gigapascals. If we get down a little further and we get to like carbon fiber, kind of down here at the bottom, we can see that carbon fiber has two numbers, because again, it depends on, it's not an isotropic material, it depends on the direction you're pulling it in, but carbon fiber can be up to 3 times as stiff as aluminum when you pull it in the right direction, and when you pull it in the wrong direction, it's less stiff than aluminum. So that's kind of why carbon fiber is like a harder engineering material to design around. But you get incredibly stiff materials like carbon nitride there, which is more than 10 times as stiff as aluminum, and you get to something like the human bone, which is kind of gross to think about, but yeah, your bones flex under force, and they're like a third or a fifth as stiff as aluminum. I'm bad at math in my head. So again, to talk about this elastic region, and we mentioned this earlier, that there was plastic deformation and elastic deformation. So for all materials, while you are in this linear region where the slope is flat, if you relax the force off it, so like we're doing our test, we go up, 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 up the line. If we then take the force back off, the strain will go exactly back down that line. Like we're walking back down, and we'll get back to where we started, and there's no permanent shape change. That's the other thing to kind of keep in mind in the elastic region. Now there's an end to the elastic region at some point. And if we remember our stress strain curve for earlier, it goes linearly up for some region, then the curve gets kind of wonky and changes shape, and there's other things that happen. We won't dive into those too much, but when you ask about like how strong is a material, and people will say, well, steel is stronger than aluminum. What are they actually talking about when they say that? And if you're not an engineer, people can often confuse themselves and say different things or mean different things. Generally, I think most people are referring to the yield strength of the material when they talk about it. And so the yield strength is the amount of stress, sigma sub y, that a material will experience before leaving the elastic region and starting to permanently deform. So just to kind of spell that out, if we repeat our experiment and we go dot, 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 up the linear portion until we reach the yield stress, and then we apply some more stress, the material will go into the nonlinear region over here and start plastically deforming. If we then remove the stress, if we take the load off, the material will relax backwards on the same slope that it went up on. It'll relax along the elastic slope, but at the end of the day, it won't return to zero. It will return with some amount of permanent shape change. Permanent. Oh my God, my handwriting is terrible. And that's what we mean by plastic deformation. So there is a second definition for the strength of a material, and that's the highest point that is ever reached on this curve. So if I went over here and I said the absolute amount of stress that I could put this object under before it snapped, that's the ultimate strength. And generally what happens with materials is as you start to stress them, most, at least engineering materials and the engineering metals we work with, do a thing that's called strain hardening, where the material actually gets a little bit stronger as you deform it and resists further deformation, which is why like the stress continues to go up through the portion between the yield strength and the ultimate strength. Once you get past the ultimate strength, failure tends to be runaway, where the thing just rips apart. So you'll see a material kind of stretch and deform and take the load, and then you go a little bit more, and then suddenly it's a runaway quick failure. That's what the ultimate strength represents. And so there's two definitions when we talk about strength for a material. Again, strength is like stress and strain, where it's one of those very defined words within engineering. But chart in the top right there is showing the different strengths of different types of materials. We'll zoom in on that for a second. And you'll see that like ceramics can be much stronger than metals, which is why like tank armor is often ceramic. And the fanciest cutting tools that we use for like machining are often ceramics nowadays. Composites, that's kind of like fiberglass and carbon fiber, but it is important to know like this is a logarithmic scale. So like going up one line is going up a factor of 10, and things cover very wide ranges. There are very weak metals and there are very strong metals, but general ranges of what strength looks like for different materials. Okay. Ductility and toughness, two other major things to talk about that are shapes of this curve. So people will often say like, oh, brass is ductile or copper is ductile, and that makes it easy to work with. And you might hear that like hardened steel is not ductile and it will snap. And ductile is the antonym word to brittle. So if something is ductile, that means it will change shape a lot. Like it's easy to work with. It's like clay. Something that is brittle, we can't change its shape a lot. Like it will resist us, and then it will snap very quickly. And so what this chart on the right is showing is the alloying of iron with carbon. And as we add carbon to iron, we change the mechanical properties of it. And what we do is we make the material, one, we make it stiffer, and two, we make it less ductile as we add it to it. So pure iron is actually a very ductile material where the distance from its initial position to where it actually snaps over there is a very far distance. It can see a lot of strain before it snaps. And so ductility is typically written as maximum strain that something can experience before actually separating into two different pieces. And it can be all over the place. A very non-ductile material here, like tungsten carbide, 0.05% deformation before snapping. And then rubber can stretch to 9 times its original length and then and still not have snapped. Like it'll just kind of goose out. So that's ductility. And now toughness is something that often comes up that's a little funkier, and people say, oh, well, titanium's the toughest metal. Well, if we actually look at strength, titanium's not the strongest metal. So what do people mean when they say toughness? Well, toughness is the amount of energy that a material can absorb. And toughness actually comes from the area underneath the stress strain curve. And if you actually work out the units on toughness, it becomes energy per unit volume of the material. And the toughness, if you're really thinking about it, is if I wanted to rip this thing apart, how much energy would it take me to rip it apart? And like, well, rubber can stretch really far, so I have to work over a really long distance to pull the rubber apart, but the rubber's not very strong. So if we draw like rubber's curve down here, rubber's curve is way down here like this. And well, steel, it's very, very hard. It can have a crazy high stiffness to it, but I actually don't have to push very far to get it to snap. Force times distance is energy. And so the material that is both stiff and ductile is the toughest material. And generally, like titanium's a very tough material. Here are some examples of, on the left, toughness of materials, and on the right, the maximum elongation that material can go under for different kind of classes of materials. And you'll see that generally they correlate pretty well to each other in that most tough materials are also ductile materials, but not perfectly, because again, like it's the combination of strength and ductility that makes toughness work out. But metal alloys are extremely tough and used a lot. Like one of the problems with carbon fiber is like if you use carbon fiber for the crash structure of your car, it can end up absorbing less energy than say, deforming steel in that same region could. And rubbers can even be slightly better, but tough materials see limited use in particular engineering domains where we care about like absorbing energy in something like a crash. When you actually go to like pick a material to use, the right material depends on application, and it depends on a lot on cost usually. Like there's a reason that houses are still made out of wood, and it's because wood is very cheap relative to the strength that it provides. Like, yes, we have better materials, like aluminum is a better material, but the cost per kind of unit of performance that depends on your application matters a lot. And it's good to know as you like become an engineer that metals are over here and composites are over there and ceramics are over here. And there is usually a very right class of material for your application, and then lots of devil in the details as you dive into it. And there are fundamentally higher performing materials than other. It's not like there's a conservation of goodness of material. Weak sand is terrible, don't use it. And we have very high grade aluminum. Generally though, what you'll find in engineering as you go out there is that cost becomes the great normalizer. So if there is a material that is super strong and you really want to use it, generally it's pretty expensive. And it's why like we want to build embankments for like the highway. Well, we build them out of dirt because it's dirt cheap. That comes up a lot. So um, now that we've kind of talked about the shape of the stress strain curve, and we understand um, how materials kind of go through this process where they elastically deform and then they plastically deform, and then when we remove the load they can kind of come back to their close to their original shape, or they descend back along the original slope. um, we'll kind of revisit this concept of what the uh, lattice structure really means. And so again, like metals really do form these lattice structures, and these lattice structures have very regular crystal repeating patterns. And this crystal kind of repeating pattern actually explains an enormous amount of why materials deform when they deform. Let me see. I'm just going to check my next slide. Yes. Okay. So this is the really important diagram to understand, which is when a material breaks apart, generally what happens is not all of the bonds in one layer of the material rip apart at the same time. If you actually think about how much force it would take to simultaneously rip every single bond in one layer of that crystal lattice, it's an enormous amount of force. It's an incredible amount of force. Instead, what happens is that defects in the crystalline structure, and we call these defects dislocations, those defects become mobile and start to move. So if we imagine there's like we have some I'm just going to use the diagram here. What this picture is showing is one individual bond snaps, and it snaps here in kind of this second picture, and this bond becomes free, and the atoms in the material want to form a bond. They are more stable when they form a bond. And so if there was, a guy hanging out over here that's available for it, this guy is going to jump his bond from the atom next to him to the atom on the other side of him. That is the easiest thing to have happen inside of one of these materials, where it's very hard to like completely just rip a bond apart, but it's pretty easy to make one atom move its bond from the neighbor next to it to the neighbor to the right. And if you repeat this process a lot, like once one guy has moved over, well, the guy next to him now wants to move over, and then the guy next to him wants to move over. And you can kind of think like, oh, well, all the atoms are shifting in one direction. Another way to think about it is there's this defect in the crystal, and we call that defect a dislocation. That defect will start moving to the right, and the defect becomes mobile. And this defect becoming mobile is the actual mechanism by which plastic deformation of the material occurs. What makes defects, dislocations, become mobile is shear stress. And shear stress is when there are, like if we imagine a plane like this, when there are forces that are aligned to the direction of that plane, that are trying to slide the material apart, like scissors coming in shear through the material, those shear forces produce forces inside the material that make these dislocations want to move. And when these dislocations do move, you get plastic deformation. Other thing to think about, like when we forge steel, like blacksmiths stick steel into their furnace, and then they come out and they hit it, and somehow making the steel hot makes it easier to change its shape. That's also kind of explained by this model, which is, each one of these little atoms is vibrating around willy-nilly, wildly. The hotter the material is, the easier it is for it to just kind of randomly shake to where it bounces over closer to its, the neighbor next to it, and can form a bond with that person. And so when you get materials so hot that they actually become just completely freely able to change bonds with their neighbors without needing any force, well, you melted it. That's what a liquid is, where the atoms in a liquid are still holding on to their neighbors. They're still bonded with their neighbors, but they're really freely able to exchange which neighbor they're kind of connected to at a given time. So again, just building a mental model for the intuition here. There is a really amazing YouTube video. I'm not going to pull it up in this recording, but I encourage you checking out Steve Mold's video on ball bearings showing this phenomenon. So what this picture is actually showing is a bunch of ball bearings stacked together, and you'll see that they form these crystal lattices, and you'll also see that it's not one giant crystal lattice. In fact, as the ball bearings kind of get randomly laid out, you see these regions where one individual crystal forms, and all of the ball bearings inside that are aligned to some axis. And within like this exact same thing happens within metals, and we call these grains. We call these individual crystals within the metal. Metals are generally referred to as polycrystalline materials, and you can see that between these two grains where I've kind of drawn those lines, they're at slightly different angles to each other. And the crystals will kind of form in just random orientations as the metal is produced. Well, as we apply shear stress to this crystal lattice, what will happen is these individual defects in the crystals, like these spots here, 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 they become mobile, and they'll start transitioning, and they'll travel over until they get to a crystal boundary or they get to another dislocation, and then they'll usually stop. That's why strain hardening happens in our curve, where like it goes linear up and then it gets harder. Well, as the shear stress gets hard enough that dislocations start to be mobile, the dislocations that are easy to move around start moving. And like say this guy's easy to move around, well, at some amount of force, he'll just go, and he will continue to move in some direction within the crystal lattice until he hits some boundary where he's not able to move. And then it will take slightly more force applied to the material, take more internal stress to get the next guy to move in the direction that he's going to move into it. And so that's why like deforming the material a little can make it stronger. You find the dislocations in the material that are more mobile than others, and you push them until they reach a boundary. So then when the material actually like falls apart and runs away and snaps, well, that's so many dislocations moving that they start piling up at these crystal boundaries, and piled up of a bunch of these dislocations at a crystal boundary can start to form a crack. And then that crack can propagate, and the crack can get bigger and bigger and bigger by snapping one kind of atom at a time through that crack until the material actually snaps apart. So knowing this and understanding this phenomenon explains a ton of the things that we do to steel to affect it. So when we do a thing called annealing on steel, which is if we deform the steel a little bit, totally fine. If we deform it more, it will snap. Well, that makes it really hard to make things in certain shapes. So we find that if we deform it a little bit and then we heat it up, those crystals will kind of regrow and reabsorb some of the dislocations that have moved around, and we'll be able to then deform the steel more after we've done that. So you can anneal steel to heat treat it and be able to deform it more and increase the effective ductility by getting it almost molten for a little bit and letting it heal. It also means that controlling the number of grains that are present in the crystal, the size of those grains, and what type of grains those are, is what affects the material property. And like when we add carbon to steel, what we're doing is we're encouraging the growth of particular types of grains that have the properties we like. So understanding this kind of crystal lattice idea of how these dislocations move explains a lot of what's going on with heat treating steel and adding carbon to it and doing these other things. So this is a phase diagram for steel that kind of shows the particular types of crystals that like to form at different combinations of percent carbon and temperature. And when we're actually like making an alloy of steel, a lot of what we're doing is pushing the steel somewhere through this curve through some heat treatment process and introducing carbon to get the particular crystals that we want to grow in the right shapes and in the right way. And by doing that, we get stronger steels or stiffer steels or whatever material properties we're going after with it. Not super important to dive into the details of that, and I frankly can't explain the details much more than that. But a good thing to know. The last thing is like quenching steel, like samurais forging the sword back in the day, and then they shove it into a bucket of water to make the steel hard. The reason that we do that is it's a way to trap the crystal structure in a way that we want it to, whereby quickly cooling the steel we make the crystal structure lock into the place it's at right now, instead of, if you gradually cool the steel, like if we gradually went back down one of these temperature curves, as it passed through the different phases, like all the austenite that we might have had, there'll be no austenite left, because the austenite will gradually all convert to perlite and ledeburite. I don't know ledeburite. Yeah. As just like a random aside, here's the thing to like know. You'll hear this word that like stainless steel is sometimes magnetic, and if you look up like what stainless steels are magnetic or not, you'll hear that austenitic stainless steels are the ones that aren't magnetic. Well, here's what austenite is. Austenite is a particular crystal grain of iron and carbon that is present at some concentration in different stainless steels. And so the more or less austenitic a stainless steel is, the more or less magnetic it can end up being. So again, I did things slightly out of order based on my slides, but here's strain hardening explained again. The easy to move dislocations move, and that makes the material temporarily harder. So we now understand stress, we now understand strain, we now understand yield stress, and why the yield stress matters for kind of asking our questions. So we're going to go back to the original questions at the very beginning of this, like what do we want out of mechanics of materials? We want to know when objects will fail, and we want to know what shape they'll change to. Well, we actually already know everything we need to know from strain to know how objects are going to change shape, at least very well within the elastic region. We just have to figure out what the internal stresses are, and then the corresponding shape change will just be the shape change produced by those stresses within the material. But we haven't really answered this question of when do objects fail to what I would call like a satisfactory level. And I think the important part now is we have to kind of go back to that Cauchy stress tensor, and we have to talk about maximum shear stress and how maximum shear stress comes about. So if I have a solid steel cube and I throw it to the bottom of the ocean, and it's now under immense pressure. There's millions of pounds of force being applied to all the sides of that cube. Does the cube change shape? And the answer is no. That cube will be a cube at the bottom of the ocean. It will, in fact, I believe, I'm very sure about this, it will be a slightly smaller cube. Like it will have compressed from the pressure forces on it. But if we bring it back to the surface of the ocean, it'll pop back right out to the same shape again. No plastic deformation of that material is possible, regardless of how much uniform pressure we put it under. So we could drop a steel cube into, and I'm again, like physicists will hate if I said this, an infinitely deep ocean. Like if we just kept uniformly increasing the pressure on all sides of that cube, it'll still never change shape. And the reason for that is that the thing that determines whether plastic deformation occurs or not is shear stress. And when there's uniform force on all the sides of a cube, you'll find that there are no shear stresses. So if I have a cube like this, if I push really hard on this side and if I push really hard on this side, eventually that cube would fail. But if I push really hard on all three sides with the exact same amount of force, no shear stresses will ever be produced and the cube won't change shape. So we have to kind of go back. We glossed over shear stress at the beginning. We have to talk about it in more detail now. So we're going to stop talking about cubes and go back to talking about squares, because I think it's a little easier to understand when we talk about the individual little squares instead of cubes. Like 3D's hard, but shear stresses act kind of along the faces, and normal stresses act perpendicular to the faces. Normal stresses try to change the shape of that cube in actual like length, and the shear stresses kind of try to change the angles of the cubes. And we can imagine, right, if we had some kind of shape here and we pushed it to the side and it deforms to be some kind of bent thing like this, that's a terrible drawing. Well, if we think about what happened to each of the little bonds in the each of the little planes, like we start with individual cross sections here, well, those cross sections kind of become trapezoids. They are no longer, these lines are no longer perpendicular to each other as the like little cubes that made up this thing change angle. Shear stresses try to make the sides of the faces change angle. And what really matters here, let me see what my next slide is to decide where I'm going to talk about it on this slide. I may be doing things out of order again, but I'll zoom in down here. The important distinction that's really hard to hammer home, and why we're going to go back and talk about the Cauchy stress tensor again, is that the amount of shear stress that you find when you ask about what the stress is in something depends on the orientation you ask the question at. So we're going to go back to our really early example that we did, where we were just pulling on like a 1 centimeter by 1 centimeter square rod with some amount of force. So we're doing that again, where we're just pulling on it. If we talk about a cube, where that cube is in the middle of the material and it's aligned to the direction we're pulling in, and we try to solve for static equilibrium kind of along that cube, we'll find, well, that cube is sitting here, and some like n divided by a has to be occurring over here, so there must be some n divided by a over here to balance the forces out. Great, totally fine. That cube is under 100% normal stress. But if we just simply change the coordinate system, and instead of drawing that cube so that that cube is aligned to the stress, we draw that cube to where it's 45 degrees to the stress. And we say, okay, well, static equilibrium says sum of forces must be zero. If we imagine that little cube, what ends up happening now is that there has to be some amount of force pushing down like that. There has to be some amount of force kind of pulling back this way to counteract it. And there has to be matching forces on these faces to make there not be a y component from it. And we find that that cube at 45 degrees to that same force is seeing nothing but shear stress. And there actually ends up being no normal stress on the cube at this point. And so the critical concept here is that the amount of shear stress kind of depends on this question of what is the orientation of the cube. And this is why we get back to the Cauchy stress tensor from earlier. And so if we take the full Cauchy stress tensor, like we just pick an arbitrary coordinate system, we will find that there are these terms on all the faces for whatever coordinate system we ask for. But we'll also find that no matter what the forces are, there will be some orientation of that cube to which there are no shear stresses. And we call this the principal stress of that tensor. And there is a mathematical way, we're not going to dive into it right now, that you can solve for the principal stresses inside any for any given cube. And basically the way to think about this is like if I have some little square that has a combination of shear stresses and normal stresses acting on it, there is guaranteed to be, there must, by kind of the laws of mathematics of this stress tensor, an orientation that I could draw that at where it ends up with only normal stresses. And we would call this sigma x, and we would call this sigma y, and we would instead call this sigma 1 and sigma 2. And so they're not aligned anymore to like our fundamental coordinate system. They're aligned to the principal stress that is going through that individual part. And what is important about this is that to then ask what is the maximum amount of shear stress that is occurring at that at the kind of worst case location, that it is always this formula on the left here of the whatever is the largest of the principal stresses minus whatever is the smallest of the principal stresses will be the maximum shear stress that could be occurring at any orientation on that cube. And to maybe dive back for a second again, like when we pull on this rod, from earlier, where with this cube at 45 degrees was where the maximum stress is. When we actually pull on this rod and this rod fails, how this rod fails is that crystal boundaries kind of aligned to this 45 degree plane. You start getting dislocation movement on these 45 degree planes that cause plastic deformation there, and a phenomenon occurs, which we saw here. I'm going to go way back in the slides briefly. If we go all the way back to when we first saw the stress strain curve diagram, there were pictures of it right here. This is called necking, where the material is getting thinner, and it's getting thinner in a conical direction, and that's because the maximum shear stress is occurring on these 45-degree planes, and the material is moving in those directions there. Even though we're pulling entirely in normal stress, we get maximum shear stress on a different angle. And so back again, what's really important about this is that if these three principal stresses are the same, you can have an enormous amount of stress in the material. The material can be under ludicrous amounts of stress, but it won't plastically change shape at all. Plastic deformation occurs at a maximum shear stress condition, and if the maximum and minimum principal stresses are equal to each other, there is no shear stress. Weird, hard thing to rationalize, but important to know when talking about stress. Oh, and I had a slide that I was supposed to do this on. So this is just explaining necking, that at the plane of maximum shear stress is where the deformation will occur. So the maximum shear stress explanation for failure is, again, what is normally encountered in engineering. When we hear that the yield stress of aluminum is whatever, I don't remember what it actually was from the size, but let's say it's 68 gigapascals, or maybe megapascals. I don't know. Don't quote me on this. What they mean is that is the maximum shear stress that will occur to actually have that failure happen. Generally in engineering, we don't actually use just maximum shear stress by itself. There's this slightly fancier version of it called the von Mises stress criterion. And if we're really just plotting axes here of kind of sigma 1 versus sigma 2, maximum shear stress predicts this kind of rhombusy diamond shape inside. Von Mises is just this elliptical shape that's slightly outside it, which ends up being slightly more accurate. The formula for von Mises is down here. You will always learn von Mises stress criterion, and that's generally the best accepted for normal engineering way to predict material failure in standard materials. So we dove through that pretty quickly. Okay, I'm going to wrap up the last bit of the class here in a hurry. One of the things to talk about with stress that is incredibly useful and why we use the Cauchy stress tensor is that stress is a linear system. And what that really means is if I have some beam that's sticking out here, and there are three forces acting on it, and I want to talk about the net stress at some point related to it, I don't actually have to simultaneously solve for all three of those forces at once. Instead, I can pretend two of those forces don't exist, solve for one force, then solve for the second force by itself, then solve for the third force by itself, and then the solutions of solving the problem decomposed like that will exactly add together. So the Cauchy stress tensors produced by, I'm going to put a bar over it to say it's a tensor, by decomposing the problem into one of the forces plus the second one plus the third one. I shouldn't have used the little threes. Ignore the little threes because those subscripts look like principal stress is not what I was trying to say there. But all of that to be said, we can decompose the problems into individual forces, solve for those forces, and then assemble the final solutions together. So that's a lot of what you'll end up doing in an engineering class is some hand calculations where you've got a whole combination of forces and you have to figure out the stresses at different points in it. Since we're a little low on time, I'm not going to dig into massively solving these, but these are again kind of example problems that you would be solving for at the end of mechanics and materials class. Determining deflection at the end of a beam with this, and this is again a compound load problem where we've got all sorts of wild stuff mixed together, but if you break it down into individual forces at a time, it's not that hard to decompose. Let me see. We'll leave it there. I won't dive into actually tackling some of these example problems in detail. It's kind of nice to see the mathematics broken apart, but there are solutions for that online that you can kind of watch through, and it ends up being a lot of statics. To really, like, the hardest part in doing any of those is figuring out what the forces are going to be at each of those internal points. Um, Key takeaways, though, for understanding mechanics of materials here: stress and strain. Let us talk about force and deflection in shape independent ways, which is incredibly useful. Every material that we work with has some fundamental properties of that material, like strength, stiffness, and ductility, that are almost always given in units of stress and strain. So, like, you have to understand stress and strain to even understand what those material properties are. There are lots of fun ways to modify those material properties. Finally, like, when do materials plastically deform or snap? It's all determined by the maximum shear stress that's going on in a material. So we have to figure out all of the stresses at an individual point. We have to figure out what the principal stresses are then. So find all the stresses going on in some coordinate system, convert those to principal stresses, compare the highest and lowest principal stresses to determine out the shear stress. That's what really matters when we're talking about a material failing. And it's important to, like, deeply understand these concepts so that you have intuition for them. What I will really say is, if your engineering class in college is anything like mine, you will be taught an enormous amount of hand calculations. You will enter the real world and you will never do a single one of those hand calculations again. I do them in my head for, like, mental. I don't know if I've ever actually done the calculations where, like, I signed off on the result at the end, because computer analysis has completely replaced this field. Finite element analysis, that's like actually breaking the shape into a bunch of little cubes and then saying what would happen to each of one of those little cubes, is a incredibly good solution. It works way better than hand calculations, and there's amazing software for it all over the place nowadays. So in the real world, I think mechanical engineers almost always lean to finite element analysis, but you need to know the fundamental knowledge to know how much to trust your finite element model and to know how to do the finite element model right. But like, real world skill that matters here is actually using the finite element analysis software. To use it right, you need good intuition of these concepts. But we'll end it there. So thank you. I hope that was useful, and catch you next time.